Good morning, everyone. Welcome to the fifth lecture on relativity. Let us begin with this. In the previous lecture, we had seen something about the Galilean transformation, and we have learned about if a frame of reference is moving with a given velocity, then how does the new coordinates will represent? We have seen what is the velocity of the particle, what is the position of the particle, and so on. Suppose if a particle is moving with a velocity nearly to light, then in that case, what could be the position and the time vectors? How does it differ? And based on this, we saw that the time will not be the same in both the cases. It will definitely differ. And in the third lecture, we saw about some of the important relativistic effects. One of them is known as the length contraction, wherein you have a particle. Let us say this is a particle. The length of this pen is seen to be, let us say, around 15 centimeters. Now, when it is moving with a velocity nearly 0.8 or 0.9 c, then the length of this will not be equal to L0 or 15 centimeters, but it will be lesser than that. Could be around 8 centimeter, 9 centimeter. It appears to us something like this. And then we also seen about time contraction. And after this, we looked at some of the numericals related to length contraction, time dilation. And these are some of the excellent numericals that I have so far found, wherein the parameters are so confusing that you should first understand where to put length, where to put the proper length, where to put the proper time, and so on. So as a result of it, I made one complete lecture only on this, which was published last week. Okay, now let us move on for today's lectures. So today's lecture will focus on frames of reference, difference between the absolute and relative frames of reference, and we'll also look at what you mean by proper length and proper time, which is nothing but a repetition of what we have seen earlier also, because this is very important for us to understand the rest of them. Euclid geometry cannot be used in the space-time. For example, Euclid geometry is one wherein you have a rectangular coordinate system. Okay, but here you will not be able to use it over here, because when the particle is moving with a speed nearly equal to c, the rectangular coordinate system itself becomes invalid. It's of no use. Then you have invariance of space-time interval. So you cannot say length is being constant or time is seen to be a constant. Both of them change in such a way that we define a new quantity known as the space-time interval. Let us see what do you mean by space-time interval, how do you write it across, and so on. How do you verify, and what is the invariance? This is the only thing that does not change when a particle is moving at a relativistically higher speeds. And then we look at a few numericals based on this. Okay, now let us look at this example over here. So as you see here, there are two cars which are moving side by side, one of them to an external observer. If I look at an external observer, it appears that one car is moving at the speed of around 40 km per hour. Okay, let us say. And the other car is trying to overtake, the white car is trying to overtake it, but it is moving at the speed of, let us say, more than that 40 km per hour. It could be 45 km per hour. For a person who is sitting inside the first car, car 2 appears to be overtaking him only with a speed of 5 km per hour. So what's happening over here? It's a relative frame of reference. Okay, so therefore, when we talk about speeds are not same because the reference frames are different. Okay, and none of the reference frames are absolute. What appears to be something like higher velocities, in your frame, it may not be higher velocities. It appears to be, yeah, difference between these two velocities would be much lesser. Okay, next, let us look at one more example. So in this example, as you see, there's a car which moves from one end to the other end on the road. There's a person who is standing on the right side. Okay, so on one side, and then he observes that the car is moving towards the left. But for a person who is standing on the opposite end of the road, he observes that the car is moving towards the right side of the road. Okay, things look different when looked at different perspectives. So as a result of it, it's once again not one and the same. Let us look at one more. So quantities that do not change in inertial frames. Whenever you have an inertial frame, what do you mean by inertial frame? Inertial frame is something like a frame which does not have experienced any force, which is either at rest or with respect to an observer, it is moving at the same constant velocity. Now shown here is something like a photon that gets reflected from a mirror, and the distance moved by the same photon is the same for both the stationary observer and as well as the observer in the spaceship, because both of them are at rest, because the spaceship is in rest now. Okay, now what could happen if the spaceship is moving at a velocity towards the right hand side? Now as you observe there, the photon is also trying to move away from it. It gets reflected from the second mirror and comes back to it. Now let us watch one by one what's happening over here. Distance traveled by the photon. Let us look at that. You see, the distance traveled by the photon is seen to be shortened in a moving frame. See, it travels a very shorter distance over here. But you look at the same in case of a distance traveled by a stationary frame. It appears to be much, much larger, right? For a person outside it, it appears to be much larger. In a similar way, let's focus on the time over here. The time as shown for the stationary observer is around 1.2 seconds. Okay, but if you take the same thing, okay, if you take the same thing there, okay, and you observe that the time taken is around 1.1 second. So which means what? The time has reduced for a person who is inside a space vehicle, and for a person outside it is different, right? Therefore, so length and time changes in moving frames is what you have learned in case of your length contraction. I'm just repeating the same thing over here. Thus, the universal truth is that length changes, distance measured also changes, time changes, duration changes. In fact, the point which you keep, pixel, okay, coordinate, that also changes. The simultaneity cannot be observed. Okay, so this is what is the universal truth which we actually know about what is the space and time. And if we are moving at a higher speeds, this is what is to be observed. Now, thus, a coordinate is not well defined in a moving frame. Okay, so what is defined as a coordinate, as you see here, okay, is appears to be at a different point in a moving frame. In fact, we will see one such example, two such examples, which shows you how does the coordinate change and what is the new coordinate if you are observing the coordinate from a moving frame. Okay. Okay, shown here is a coordinate system wherein an x and y axis is being shown over here. Okay, now let us consider a point. Let us consider 2 points. This is your point A. This is your point A, and this is your point B. Point B over here. And if I want to find the length, what do? I just draw a line over here, and then I find out what is the x coordinate of this one. Then I find out what is the x coordinate of this one. Then I will do x2 minus x1, x2 minus x1, the whole square. Similarly, I will find out what is the y coordinate of this one, y1, and I will find out what is the y coordinate here, which is y2, plus y2 minus y1, the whole square, is equal to length square. This is what we actually do it here, right? Okay. Now, this is in case of a stationary frame. But if the frame is moving with a higher velocity, okay, and then from the moving frame of reference, if you are watching this, then in that case, this value, the length PQ that I had mentioned over there earlier, okay, will not be the same. If I take, for example, from here, if I consider x prime, y prime, z prime are the coordinates of these points, okay, from the moving frame of reference, in that case, your delta x dash square plus delta y dash square plus delta z square will not be equal to delta x square plus delta y square plus delta z square. What is this now? This is nothing but a Pythagorean theorem applied in a 3 dimension, right? So this is also a Pythagorean theorem applied in 3 dimension. Usually it should be applicable, but when you go at a higher space, this is higher speeds, then definitely this equation is inapplicable. Similarly, the time duration at which you are measuring these two will also not be applicable. Let us say these are 2 different events which are happening after a time delta t, then your time duration that you measure here, the time duration that you measure here will not be the same, okay, will be differing, right? So thus, if I want to be the same, so what is that I need to do? If particles are moving at very high speeds, okay, and the spaces are being interconnected, then definitely what can happen is this delta x square plus delta y square plus delta z square will not be equal to delta x dash square plus delta y dash square plus delta z dash square. But there will be one more quantity which is shown over here. That quantity is you put a minus c square delta t square. Thus, the quantity, namely, so delta x square plus delta y square plus delta z square minus c square delta t square is called as a space-time interval. So in essence, if I want to just put it across here itself, I can tell you that your delta x square plus delta y square plus delta z square, which is nothing but the length of a line in 3 dimension, okay, which should also be equal to delta x dash square y dash square plus z dash square. That's what we have seen in Galilean relativity, if in the moving frame. Okay, in special relativity, though the lengths cannot be same, but if you consider this minus c square delta t square, okay, on both the sides, then definitely that factor, whatever you have, delta x square plus delta y square plus delta z square minus c square delta t square will be having the same value in both the moving frame and as well as in the reference frame. Okay, so that's what it tells you. So this is what we call as a space-time interval. Now currently for time being, what we do is we'll consider the particle is moving only in a straight line. If I say it's moving in a straight line, your delta y dash and delta z dash, and so delta y and delta z will become 0 because there's no change in the y and the z coordinates. And as a result of it, your space-time interval would be given by delta x dash square minus c delta t square is equal to delta x square minus c delta t whole square. Now, what does it mean? Why are we doing all this? Okay, still it is scratching your head. Just wait for a moment. We'll do a problem. Then you will get to know, okay, why are we doing all this? Okay, now let us do this particular problem. Lightning strikes a point on the ground frame S at position x equal to 3500 meters and time t equal to 5 seconds at x equal to 3500 meters. So let me write down the coordinate system first. At x, this is your 3500 meters. It strikes it at t equal to 5 seconds. Okay, this is at t equal to 5 seconds. Then determine where and when the lightning struck according to a rocket that flies past the ground at speed of 0.8 c to the right. Okay, to the right, there is a rocket which is moving over here. It is moving at a very high speed of 0.8 c. It is asking you what is the coordinate of the lightning. See, lightning here falls exactly at this point. Okay, but we do not know where does what according to the observer in the rocket sees this. Now, which is your proper length? Which is your proper time? Proper length is nothing but this value. This is your proper length. And what's your proper time? Proper time is this value, t0. Okay, and now we need to find out what? We need to find out, determine where and when, which means what? You need to find out x dash and t dash. Now you see, when this happens and the rocket is moving like this, where do you see the lightning to be? Lightning will be seen behind us, right? So therefore, what equation should I use? I should use x dash is equal to x minus vt multiplied by gamma. Okay, now let us substitute all the value. What's the value of x? 3500 minus v. What is v? V is 0.86, 0.86, and t value is not known to us. How do I find the value of t? T is equal to 5 seconds. It's given here. T is equal to 5 seconds into 5 minus, into gamma. What's the value of gamma? Let us write down this. Gamma is equal to 1 by root of 1 minus v square by c square. What's the value of v? V is 0.86, which should be 1 by square root of 1 minus 0.8 c square, 0.8 c the whole square divided by c. So this c and this c goes away. So I get this as 1 by square root of 1 minus 0.64, which should be equal to 1 by square root of 0.36. And now 0.36, what's the unit, the square root of this one, which will be 1 by 0.6. 0.6 would be 6 by 10, which would be equal to 5 by 3. This is the value of gamma is got. Now where will I substitute here? I will substitute it here, in the gamma here, right? So thus x dash will now be equal to 3500 meters minus 5 into 8, 4, minus 4c, right? 5 into 4, 4c into 5 by 3, into 5 by 3. Okay, now, okay, so this value comes out to be minus 1.99 into 10 to the power of 9 meters. Okay, so which is nearly equal to minus 2 into 10 to the power of 9 meters. Which means, where is this particle actually? See, this was the coordinate. This was the place where lightning struck to it. But as the rocket moves over here, the time is seen to be around minus 2 into 10 power 9. Which means what? This point has got shifted to here. Somewhere over here shifted, right? Now let us find out what is the time it takes. So we already found out the value of x dash here. Now let us find out the value of t dash also here. So we know relativistic equation for time is given by t dash is equal to t minus vx divided by c square multiplied by gamma. The value of gamma we already know, which is 5 by 3. So I just substitute v 5 by 3 into t. What is the time here? In the regular frame, it was stationary frame, it was 5 seconds. 5 minus, what's the value of v? 0.8 c multiplied by x. What is the x value here? It should be 3500 divided by c square. Okay, so this square and this square goes away. So you get this as 5 by 3 into 5 minus 933.33 into 10 to the power of minus 8. So this is what I get over here. Okay. So now let me simplify this. When I simplify this using the calculator, I am getting this as 8.33 seconds. So this is what I'm getting over here. So of course this will be negative time over here. See, we are looking at the negative time. What does it mean? Can the time be negative? Time obviously here is negative, which means that after the rocket has passed away from the event, 8.33 seconds after it passed, this event occurs. That's what it tells you. Okay. So now we have got this value. What's the next thing? So we have calculated the values of x dash and t dash. Now for x is equal to 3500, t was seen to be 5 seconds. And for x dash is equal to, now what's the value of x dash? We just found out earlier, minus 2 into 10 power 9. Minus 2 into 10 power 9. Then the value of t dash was seen to be minus 8.33 seconds. See, there's a large difference between x and t over here. There are no correlation at all. Okay, because one is in the moving frame, the other one is as estimated by the stationary frame. Okay, now what we will do is, so if they are not equal, when can they be equal? What can be equal? There's only one parameter which can be equal. What is that? It is nothing but your space-time interval delta s square. What do you mean by that? Which means that if you take delta x square minus c square delta t square, let's find out what is this value. Now I'll replace this delta by x over here. So I get this as 3500 the whole square minus t square into 8.33 square. Negative t dash c square into not 8.33. This is 5 square. 5 square over here. Okay. When I do this, what is it I get? This should be 3500 the whole square minus, this is c is 3 into 10 power 9, right? Which will be 9 into 10 power 18 multiplied by 5 square is 25. Minus 2.25 into 10 to the power of 18. Okay, don't worry about the units. We'll just write like this over here. Next, what I will do is, I'll do the same calculation even for delta s dash square. What do I get over here? So here I'm going to replace this delta x by the primed coordinate. Delta x dash square minus c square delta t dash square. So when I do this, what do I get? Delta x, what is delta x? 2 into 10 power 9. So when I do the square, this negative sign will go away. So I get 4 into 10 power 18 minus, this is c into 8.33. What is c? C is nothing but 3 into 10 power 8. So 3 into 10 to the power of 8 multiplied by 8.33 the whole square. So this should be 4 into 10 power 18 minus 624.5 into 10 power 16. 0.5 into 10 power 16. Now you see 10 power 16, 10 power 18 here. I'll make this as 400 minus 624.5. Maybe I would have missed some the decimal points into 10 to the power of 16. So this should now be 400 minus 624 should be minus 224 into 10 power 16, which is closely, you see, this were nearly equal. Here it is minus 2.25. Here also it's minus 2.24 into 10 power 18. So thus you see what is covariant, what is invariant. What do you mean by invariant? That means what is not changing between the moving frame and the stationary frame. It's nothing but your delta s square. The rest everything changes, only this does not change. Okay. Now let us move on to the next question. The rocket is moving at 0.8 c past a space station. What is this now? This is your velocity v. What is the rocket according to the space station? When the rocket shows 0.6 microseconds. So where is the time which has been taken? This is a proper time. This is your t naught. Okay, where is it now taken? This is with respect to the rocket frame. This is a rocket frame. Right? What does the space station clock read at this position? Okay, what is he asking here? Where is the rocket? That means he is asking you what is the spatial coordinate and what does the space station clock read at this position? He is asking you the value of x, he is asking you the value of t also. Now usually when I want to find out the value of x and x, then I definitely have an equation like x is equal to x dash plus vt multiplied by gamma. This is what I have. But the value of x dash is not known. What will I do? What I do in this case is I'll assume, okay, that at the point when the rocket left the space station, that coordinate is x dash, which is equal to 0. Okay, so therefore I'll put x dash is equal to 0. X dash equal to 0. So x should now be equal to 0 plus vt. What is v? 0.6 into 10 to the power of minus 6 microseconds, right? Sorry, v is 0.8c. I'm sorry. So x is equal to 0 plus 0.8c multiplied by time taken. This is what vt0. So into 0.6 microseconds. This is t dash over here, right? 0.6 into 10 to the power of minus 6 multiplied by gamma. What's the value of gamma? Let us find out the value of gamma. Gamma should be equal to 1 by square root of 1 minus 0.8 square. C square by C square goes away. So which should nearly be equal to 5 by 3. We have seen this in the previous problem also. You can just take it out into. So this should be multiplied by 5 by 3. So which should now be equal to 5 by 3 into 0.8 into 0.6 equal to how much? 0.48. 8 6 are 48. 48 into this C here. So 3 into 10 to the power of 8 and into 10 to the power of minus 6. So now this 3 and this 3 goes away. The 5 into 48. How much 5 into 48? 5 8s are 44, 5 4s are 20, 24. 24, and since it's a single digit over here, I'll put 2.4 multiplied by this 10 power 8, 10 power minus 6, which should be 10 square. So this should be 240 meters. Which means what? Which means that according to the space station, according to the rocket, the position of the rocket was seen to be at 0. But according to the space station, the position of the rocket is seen to be starting at 240 meters. Right? Okay, and then now let us find out what's the value of time. Time, which time I should take? I should now, this t naught is given. I need to find out the value of small t. This should now be equal to t naught divided by root of 1 minus v square by c square. Right? Let us substitute all the values. So I'll get t naught is equal to 0.66 microseconds divided by, what is the root of 1 minus v square by c square? Root of 1 minus v square by c square, 1 by is nothing but 5 by 3. I'll substitute this one as 5 by 3. So how much will they get? So 3 2s are 0.2 into 5 will be equal to 1 microsecond. Okay, now what is that we have got? We have got the value of t. Now what we'll do is we will write down the value of x dash and t dash and x and t, and then find out, okay, the invariance. X comma t. X comma t is equal to how much? X comma t is what we found out now, which is 240 and 1 microsecond. 240 and 1 microsecond. And what is x dash comma t dash? X dash comma t dash. Let us write down this also. X dash comma t dash is equal to, what is x dash? X dash is, where is it? X dash was 0 and t dash was 0.6. 0 comma 0.6 microseconds. Now what's the next thing? Delta s square. Let us find out from here. This should be x square minus c square delta t square, which is equal to how much? What is x square here? 240 square. 240 square minus c square. 3 into 10 to the power of 8 into 10 to the power of minus 6, the whole square, which should be 240 square minus 8 minus 6 is 2. So this is 300 square. 300 square, right? Minus 32,400. Okay, I get this value. Next, what I do is let us do the same calculation here. So what is the calculation here? Delta s dash square is equal to x dash square minus c square delta t dash square. When I do this, what is x? X dash is 0. 0 square minus c, 3 into 10 to the power of 8 multiplied by delta t is 0.6 microseconds, right? So I'll write this as 0.36 into 10 to the power of minus 6 the whole square. I'll write like this, right? I have to write 0.36 only. Okay, so we'll multiply this and later on we can square this, which should now be equal to minus of 3 into 0.6 is 1.8. 1.8 into 10 to the power of 8 minus 6 is 2, the whole square, which should now be equal to minus of 1.8 is equal to how much? 1.8 square is 180, and that is 180 the whole square. Now let us write down what is 180 square. It's once again 32,400 minus 32,400. Okay, minus 32,400. Thus you see this delta s square and delta s dash square is not going to change. That means the space-time interval is not going to change whether in the moving frame or in case of a stationary frame. The value of x, t can change, the positional coordinates can change, the length of it can change, the time duration can change. What is simultaneous in one frame may not be simultaneous in the other frame. Everything can change except this. Okay? Let us move on to the next one. So consider the points A, B, and C. Okay, where is it? A, B, and C. So these are the points A, B, and C shown over here. Space diagram. Find the square of the space-time interval delta S square between each pair of points. So find out what is the distances between AB, AC, and CB. That is the value of delta S. Okay, so this is what you need to find. See, this is not using something like your distance formula. Okay, so you have to find out the value of delta S. That's why this problem was given. So delta S, let me calculate this for AC. Let me calculate this for AC square, which will now be equal to delta X square minus del C delta T the whole square. This is the formula we are going to use. What is delta X along this direction? Now what is delta X for this one here? AC, right? We want to do for AC. So this is 1 unit, 2 unit, 3 units, and 4 units. This is 4 and this is 2. So 4 minus 2 here. 4 minus 2 the whole square minus C delta T. What is C delta T here? See, don't put the value of C here. You just take it like this over here. Okay, 1, 2, 3, 4. C delta T is nothing but there is no change in the C delta T value. It should be equal to 0 here because delta T is not changing. So therefore, this should be 4 minus 2 whole square should be 2 square. So this value should be equal to 4, right? And similarly, if I want to find delta S square for AB, now what do I get once again? For AB, what is delta X square here? This is 2 here and this is 1 here, right? So this should be 2 minus 1 the whole square minus, now what is C delta T whole square? There is definitely C delta T here. See, this is your 4 units over here, this is 1 unit over here. So therefore, this should be 4 minus 1 the whole square, which should now be equal to 1 minus 4 minus 1 whole square is 3. 3 square should be 9. So this value should be equal to minus 8, right? And then delta SBC. Let us calculate this also. This should now be equal to, what is delta X over here? See this point, this X coordinate is going to be 1, 2, 3, 4. This is 4 minus, what is this X coordinate? This is 1 over here. 4 minus 1 the whole square for this minus delta T. C delta T. What is C delta T? Here it is 1 and here it is 4 once again. 4 minus 1 the whole square. So this should be equal to 0, right? So therefore, so this is the way how you can calculate your space-time interval for each of these points. So maybe in the next video, we will look into, so why do we calculate this? What do you mean by positive value of delta S? What does it mean by negative value of delta S? What does it mean by 0? And we will see all these things in the next video. Now come to an end to the space-time interval. I hope you have understood this topic clearly, and if you find this topics to be interesting and you want to know more about the problems based on this, do write back to me on the comment section, and I would be happy to do more number of such videos, okay, on theoretical concepts. And see you again in the next video. Before you leave, do share, like, and subscribe to my channel for more updates. Thank you very much.